Everyone, welcome to lecture 6 of the lecture series Signals and Systems. In today's video, we will see a short review on our focus and what we have achieved so far, and then we'll see what is Fourier analysis and give a small historical perspective of Fourier analysis. And then before ending the lecture, we'll look at the response of LTI systems to complex exponential. So let's get started. What did we see so far? I'll give a short review. So we first saw the representation of a signal x of t in terms of shifted impulses, correct? X of tau, delta of t minus tau, d tau, minus infinity to infinity. So this is a representation of a continuous time signal as integral of shifted impulses. And then what did we actually do? We passed this signal through an LTI system, right? And we represented the output of LTI system in a simpler way, right? And what did we use there? Using impulse response. H of t. So, y of t is convolution of x of t with h of t, which is nothing but x of tau, h of t minus tau, d tau, right? So far, this is what we have seen. So what is our main idea here? Our idea is we are first seeing a representation of any signal in terms of some basic signals, right? And then it is just sufficient if we just know what is the response of this basic signal to an LTI system. Using that, we can actually represent the entire output y of t in terms of the basic signal's output and the input x of t. So now, as Fourier analysis, what we are going to see? This we will see in the next thing. So what is this Fourier analysis? So it is a concept of representing periodic signals as sum of harmonically related sines and cosines or periodic complex exponential. So in the beginning of the lecture itself, we saw about this complex exponential and sines and cosines. So what they are saying is, if any periodic signal x of t, so let's say periodic signal, if we are able to represent this as a sum of sines and cosines, so sine, let me take some coefficient, sum over k, ak sine omega kt plus sum over, let's say n, bn cos omega nt. So if we are able to represent this signal, any periodic signal in terms of sum of sines and cosines, then for our analysis, it is similar to this, right? So if we just know what is the response of sine and cosine to the LTI system, then we can find the output y of t in terms of the response of sine and cosine, and these coefficients will come as it is, right? That is the main focus. Basically, to summarize, these are like our basic signals. And if we know these signals response to an LTI system, then we can, if we are able to represent any signal in terms of these basic signals, then we can easily find out the response of any signal using the response of these basic signals. Okay? So before going into all this analysis, we'll just see the historical perspective, how this Fourier analysis evolved. So that will serve as a motivating factor to actually learn this concept very well. So we already saw what is Fourier analysis, what is the main idea, and we'll see how it has evolved. So in the Babylonians' time itself, they have used the trigonometric sums like this to predict periodic astronomical phenomena. How great it is, right? So they have predicted the motion of stars, other planets and the solar systems, moon, everything based on this idea. of trigonometric sums. But where the main modern day science is starting, right? In 1748, J. Euler was the first person to examine the motion of a vibrating string. So you can see the picture of the string here. The two ends are actually fixed and you are having some kind of motion. You can see all these are harmonically related. So what it means to say harmonically related? So you have sine omega t. So what are the harmonic related counterparts of sine omega t? So you can see the frequency here is omega. So then you have sine 2 omega t. The frequency here is 2 omega. If it is such that the frequency is n omega, then they are said as to be harmonically related. So all these sine omega, sine 2 omega, sine 3 omega and so on are harmonically related. So if it is starting from sine 2 omega itself, then what are the harmonically related terms? It will be sine 4 omega t, sine 6 omega t and so on, right? So it is just an integer multiple of the frequency. That is being referred to as harmonics. So if you see here, if you take this is the first fundamental harmonic, then you can see this will be the first harmonic, right? This is the fundamental frequency, then this will be the first harmonic. So you can actually find that by seeing how many number of crest or troughs are there. So you can see here there is only one crest. So here you can see there are two crests, right? There is one crest and one trough in a single, if you take a single curve, just this dotted if you consider, here there was only one crest, here there is one crest and one trough. Here you can actually see there is one crest, one trough and another crest. So 2 plus 1, 3. So this way they are harmonically increasing. So these are actually called as the normal modes of a vibrating string. Okay. And these are also called as standing waves. So why these are called as standing waves is because it appears as if the string is standing. If you see these points, if you look at these fixed points, they are always never moving. This point also never moves. So even if in this case these points are never moving, so it appears as if the waves are standing and just vibrating up and down. They are standing in a fixed position and vibrating up and down. So they are also referred to as standing waves. So what did Euler note based on this observation? He noted that if the configuration of a vibrating string at some point in time is a linear combination of these normal modes, so is the configuration at any subsequent time. So what he actually means is, let's say this is the string and let's say it's having some structure like this. It is having some shape like this at some time t1. Then if you are able to represent this, right, let's say this is being represented in terms of, this is the x-axis and this is the vertical height. So f of x comma t. So it depends on time and the position where it is. So now it is at t1. If at t1 I am able to represent this as sum of these linear combination of these normal modes. So these normal modes, let us call it as x1 of t, x2 of t, x3 of t and so on. Okay, x4 of t and so on. Then we can actually sum them up as xk of t. And since it is at t1, this is also at t1. If this is the case, then this implies that at other time instance also it is the same. So this is what he observed and he noted. So then what development happened? In 1753, de Bernoulli argued that all physical motions of a string could be represented by linear combination of normal modes. So Bernoulli, what he is saying is, if string is in any shape, right, at any particular time, we can always represent this shape or this vibration using this summation. Okay, that is what he is arguing. But in 1759, J.L. Lagrange strongly criticized it based on his belief that signals with corners cannot be represented using trigonometric series. So what he is arguing, so if there is some signal with like this, we have the step input, right? If there is some signal like this, so this in real life it is not possible, but if you're just plucking the string, then you can actually arrive close to this kind of corners, right? So this is like a single point or discontinuity. So Lagrange is actually arguing that this kind of discontinuity, how can you represent it just by some of these normal modes? Because these normal modes are all smooth, correct? You can see all are smooth. How can you say that you add so many smooth signals to produce such a discontinuity? It seems impossible, right? So that is what Lagrange is arguing. So they were not convinced about this. And then came Joseph Fourier. So he is the main person. And we have named this method after him, Fourier analysis. So he in 1807 had found series of harmonically related sinusoids to represent the temperature distribution through a body. So in the first introduction slide, if you have seen, I have shown the map of India showing the temperature variation across X and Y axis. So it's such a body, in some body, he has found the temperature distribution which can be represented by harmonically related sinusoids. So that itself is a great improvement. And then he went one step ahead and also claimed that any periodic signal could be represented by trigonometric series. So even if it is like a discontinuity, it can still be represented. He claimed it. But there was not any mathematical development being done by him. It was only by P.L. Dirichlet in 1829 who provided the mathematical formulation and also the precise conditions for a periodic signal to be represented by Fourier series. So it also stated that yes, all practical signals can be represented by Fourier series, but there are also some conditions for a periodic signal to be represented by Fourier series. And then Fourier again went one step ahead and also he started describing aperiodic signals also as a sum of weighted integrals of sinusoids. So this one we will see in the later chapters. But for now, hold on with me. And although all these works were on continuous time signals, these were also extended to discrete time signals. And transforms such as DTFT, DFT and algorithms like FFT was developed. So this actually revolutionized the signal processing domain itself. So whatever we are going to see now is actually like 2 to 3 centuries of efforts and realizations by many scientists. I hope that this served as a good motivation for you to learn this topic. So let's now see the response of LTI system to complex exponential. So we said, okay, there is something called as Fourier analysis, where the signals, periodic signal, is represented as sum of sinusoids, right? Omega nt. So these sinusoids itself can be expressed as complex exponential. We also saw that in the previous video, right? Sine omega t is nothing but e power j omega t minus e power minus j omega t by 2j, and similarly cos omega t is e power j omega t plus e power minus j omega t by 2. So we can just combine these and write as sum m e power j omega m into t. And they should be harmonically related. Right? And I forgot the coefficients. Let's say some Cm. So what does harmonically related mean? Omega m is some integer multiple of some fundamental frequency omega. So summation m Cm e power j m omega t. So we actually state this. We'll see in the next lecture how we prove this fact. But if we say this is what it is, and as we already saw in the previous lectures, we've actually found delta of t and its response to the LTI system. And it was very useful in describing other inputs and outputs also. So here, if x of t is sum of linear combination of this complex exponential, then we want to explore what will happen when this is passed through an LTI system, right? So that is what we'll look at now. In general, we'll consider x of t as e power st. Okay, this is the complex exponential. So then we pass it through an LTI system. Let's say the impulse response is h of t. What is the output y of t? So we know y of t is nothing but x of t convolved with h of t. And here x of t is e power st convolved with h of t. So what will we get? Integral minus infinity to infinity x of tau. X of tau is e power s tau and h of t minus tau d tau. Correct? So looking at it this way, you may say that there is nothing much we can obtain from this. But let's use the commutative property of this convolution. So x of t. Now let us write minus infinity to infinity h of tau x of t minus tau d tau. So what you will get? Minus infinity to infinity h of tau is same. X of t minus tau is e power s into t minus tau d tau. So what is this? Minus infinity to infinity h of tau e power st e power minus s tau d tau. So this t is not involved in this integral. This integrating constant is tau. Sorry, integrating variable is tau. So this will be e power st. You can take it outside. So what is left? E power minus s tau d tau. So if you see, this depends only on s. After the integral is evaluated, this tau will go away. So this depends only on s. So we can actually write this as some function of s. I'm taking h of s. So we obtain y of t as e power st h of s. So can you see what is interesting here? We actually passed the signal e power st and we got some factor into e power st, correct? Some function depending on s. So this is like a eigen value, right? So we can also say that complex exponential are eigen functions of LTI systems and the eigenvalue is given by h of s is equal to this one, integral minus infinity to infinity h of tau e power minus s tau d tau. I believe you all know what is eigenfunction and eigenvalues. So if you give any input x of t to a function, if you get some constant times the same function, so the same function is appearing in the output also with only differences with respect to a constant, then it is called as an x of t is an eigenfunction of this function f, and this a is called as the eigenvalue. Okay, I'll probably put this here. Eigenfunction, eigenvalue. Okay. So now it is interesting, right? So now if it is e power j omega t, this will s will just change to j omega minus infinity h of tau e power minus j omega tau d tau. So now if x of t is actually nothing but e power j m omega t, right? So what will y of t be? If we pass this x of t through an LTI system, what will y of t be? It will be summation m, Cm remains same. You will, for each of this exponential, you will have some h of j omega, right? H of j omega, and it is m omega, and e power j omega mt, correct? And what will be this h of j omega, j m omega? It will be the same, minus infinity to infinity, h of tau e power minus j omega m omega tau d tau. So now you can appreciate the entire fact, correct? So it is just sufficient for us to know this one, right? This eigenvalue for each of this complex exponential and the x of t in terms of the complex exponential, then we can easily obtain the output. So let us see one example on this, the calculating h of x. So example on calculating h of s. Let's take a simple example. Y of t is equal to x of t minus 3. So you know h of t for this, right? This LTI system. Let's say this LTI. So what is h of t for this? This is delta of t minus 3, correct? The impulse response, impulse signal shifted by 3 units to the right. So then you can find h of s. H of s is this one. Integral minus infinity to infinity h of tau e power minus s tau d tau, correct? And this is nothing but integral minus infinity to infinity delta of tau minus 3 e power minus s tau d tau. So you know when there is an impulse like this, you know what value it will see. So this tau will just be replaced with 3. So e power minus 3s. This is h of s. So now let us say x of t is cos 4t plus cos 7t. So now we can write this in terms of complex exponential. So this is nothing but e power j 4t by 2 plus e power minus j 4t by 2 plus e power j 7t by 2 plus e power minus j 7t by 2. Now for each of this you need to calculate. So e power j 4t, this is nothing but s is equal to 4j, right? So h of 4j, right, is nothing but e power minus 12j. And then what we have, e power minus j 4t, here s is minus 4j. So h of minus 4j is e power 12j. Similarly, e power j 7t, s is nothing but 7j. H of 7j is e power minus 21j. And e power minus 70, j 70, s is minus 7j. And this will be minus 7j. And this is e power 21j, correct? So what will be the output y of t? So y of t we already saw, right? It will be in this fashion. So whatever half e power j 4t, it will remain same, and we will get h of 4j plus half e power minus j 4t, h of minus 4j plus half e power j 70, h of 7j plus half e power minus j 70, h of minus 7j, right? And we actually have these values. So this is half e power j 4t, e power minus 12j plus half e power minus j 4t, e power 12j plus half e power j70 e power minus 21j plus half e power minus j70 e power 21j. So now we can try to combine this. So this is nothing but e power j4 into t minus 3 plus e power minus j4 into t minus 3 by 2 plus e power j7 into t minus 3 plus e power minus j7 into t minus 3 by 2. And what is this? This is nothing but cos 4 into t minus 3, correct? Plus cos 7 into t minus 3. So this is y of t. This is expected, right? When this is x of t, we just want to replace t with t minus 3. Then we'll get the same answer. So this is just like a verification. So this was a simple example, and you could have straightforwardly said this is t minus 3 here. You need to substitute t minus 3 here. But for some complex LTF systems, this may not, like just substituting t minus 3 may not work out. And x of t itself may not be straightforward functions like cos 40 or cos 70. So as the course proceeds, we'll see how to solve those. So the main focus of this lecture was to appreciate the fact that continuous time signals can be represented as sum of some basic signals, and how this representation can be exploited in terms of LTI systems. In the next lecture, we'll see about the Fourier series representation of continuous time periodic signals. Until then, stay tuned, take care, bye-bye.